Can a piece of hardware do something it was specifically physically designed not to do? It sounds completely impossible, right? Well, sometimes technology has a funny way of breaking its own rules.
And that brings us to our central mystery, a CPU with no graphics chip, somehow creating graphics. Now, before we unravel that puzzle, we're going to dive into some of the real-world hardware dilemmas that every single PC builder runs into. But don't you worry, we will circle back and solve this bizarre case at the very end.
So yeah, before we get to the weird science fiction stuff, let's talk about the questions that hit your wallet first. These are the choices every one of us has to make when putting together a build, starting with the biggest one of all, your budget. Ah yes, we've all been there. You're staring at two different components, and that little voice in your head, or maybe it's a friend or a YouTuber, says, hey, just spend a little more for the better one. But is that always the right move? Let's break down when that advice is golden and when it's, well, just a trap.
Okay, so here's rule number one. If the price jump is massive for a tiny gain in what you actually do, don't do it. Just don't stretch. Take a video editor, for example, choosing between a 4070 and a 4070 Ti for pretty basic 2K video projects. That price difference is huge, but for that kind of work, the cheaper card is already overkill. You'd be paying a massive premium for power you will literally never even touch.
But here's the flip side. Let's say the price jump is smaller, maybe around 10% of your whole build cost, like we see here. And for that little bit extra, you get a component that's significantly better and is going to last you a lot longer. Now that is a stretch that is absolutely worth it. Spending a little more right now can save you from needing a whole new upgrade just a year or two down the road. So the real takeaway here, what this all boils down to, is focusing on value, not just bigger numbers on a spec sheet. You know, the smartest move isn't always to stretch up. Sometimes you should stretch down, save that cash, and put it toward another part of your PC where it'll make a real, noticeable difference you can actually feel.
And this whole idea of value leads us right into another classic showdown, choosing between a trusted, older piece of hardware versus a brand new one that costs pretty much the same. It's the ultimate battle of a proven workhorse against shiny new technology. And this chart, wow, it just lays it out perfectly. The better card really truly depends on the job you're giving it. For modern gaming, the RTX 4050 wins hands down. Newer tech like DLSS 3 and frame generation gives it a huge advantage for a smoother experience. Same thing for video editing. Its newer codec engine is just way more efficient. But for things like AI and really complex 3D modeling, that old workhorse, the RTX 3060, has a secret weapon. And here's what that really means. That VRAM, that memory, it's not just a number on a box. It's a hard limit. It's a capability. The 3060 is still so relevant because even though it might be a bit slower, that big pool of 12 gigs of memory means it can finish massive projects that would literally crash a newer card that has less VRAM. It's a practical tool that just gets the job done. Period. Okay, so we've sorted through the tricky parts of buying hardware. Now, let's talk about actually using it and bust a myth that causes so much unnecessary stress for PC users everywhere. Come on, you know you've seen it. You're deep into a gaming session, everything's going great, you glance over at your monitoring software and bam, you see that big scary number, 99% usage, probably glowing bright red, and your heart just sinks, right? You immediately think you're about to burn out your super expensive graphics card. But the reality is the complete opposite of what you think. Seeing 99% or even 100% usage while you're gaming is a good thing. It's a great thing. It means there are no bottlenecks holding it back, and your GPU is working at absolute peak efficiency to pump out every single frame of performance you paid for. It's not being damaged, it's doing its job perfectly. Now this is where it gets really interesting. Think of it like this. The dynamic up and down loads you get from gaming, that's good stress. It's like an athlete sprinting during a game. It's exactly what they're built to do. The bad stress, the stuff that actually causes damage over time, is a constant, never-ending 100% load day in and day out, like from crypto mining. That's like forcing that same athlete to run a marathon every single day with no rest. That's what causes wear and tear, not a few hours of gaming. All right, we've navigated the practical side of PC hardware, from what to buy to how to use it. Now, it is time. Let's go back to that mystery we started with and finally solve this impossible case of the phantom graphics. So let's just recap how absolutely bizarre this situation is. A user has a CPU that is specifically sold without a working graphics chip. It's supposed to be disabled.
They take out their main graphics card, they plug their monitor into the motherboard anyway, and they get a picture. They can even launch a game. I mean, it runs at a terrible 4 frames per second with the CPU at 100%, but how is that even possible?
Well, this wasn't some secret feature or a hidden Easter egg left by Intel. Nope, this was a 1 in a million technological accident. It was a perfect storm where 4 totally separate things had to go wrong in just the right, perfect sequence for this miracle to happen.
Okay, let's break down this chain of failures. First, the lock that Intel puts on at the factory to disable the faulty graphics part of the chip, it must have failed to fully click into place. Second, the motherboard's own software, the BIOS, had a bug in it. Instead of ignoring the disabled chip, it actually detected the one tiny piece that was still kind of working, the display engine. Third, Windows couldn't find an Intel driver, of course, so it just fell back on its own super basic Microsoft display driver. And finally, that basic driver used the CPU's raw muscle to draw the graphics, which is why it was maxed out at 100% just to produce a pathetic 4 frames per second. So the most important thing to understand here is this. You can't make this happen on purpose. It was a lottery-winning glitch. It needed a physical flaw in the CPU itself, a coding bug in the motherboard, and a specific software behavior in the operating system to all line up perfectly. It's an absolutely fascinating anomaly, but it's completely 100% unreproducible. So if we tie all this together, you can see a pretty clear theme, right? When you're stretching your budget, aim for real, tangible value, not just bigger numbers. When you're picking parts, remember, the best hardware is just the right tool for your specific job. When you're gaming, don't be afraid of 99% GPU usage. Celebrate it. It means you're getting peak performance. And finally, technology can fail in the weirdest, most incredible ways. And in doing so, it shows us just how complex these systems we use every day really are. And that really just leaves us with one final thought to chew on. When you peel back all those layers and you see the intricate and sometimes completely broken dance between hardware and software, does it change things for you? These components stop being just tools in a box and I think become something way more fascinating.
What if the very thing you paid a premium for, this sophisticated computer chip designed to run flat out, was the one thing you're actually afraid would break it?
Yeah, it's this fear, isn't it? This anxiety that pushing your, expensive hardware to 99% might just be asking for trouble.
It's a classic tension,
Yep.
right? Between how it's made to work and, well, how much it costs you.
Exactly. And that mindset, it's so common. And honestly, it's completely counterintuitive when you think about modern engineering.
How so?
Well, we spend hundreds, maybe thousands on thermal solutions, really robust components, sophisticated silicon. It's all designed for peak performance reliably.
Right.
But then you see that 99% utilization number and your brain just screams, whoa, slow down, you're going to burn it out.
Yeah, I get that feeling.
We really need to shift that whole perspective. It's designed for that.
Okay, so let's unpack this whole relationship. The cost, the fear, the performance, starting with maybe the biggest money trigger, the GPU budget. We're going to tackle this spending dilemma, this idea some of our source material calls that feeling you have to push for a better component, even if it really stretches the budget.
That pressure, yeah.
So when does that push actually make sense? When does it give you real value?
Because the common advice is just always go higher, right? Get the best you can possibly afford.
But we're going to argue that's often, financially not the smartest move.
Definitely not. And we can show why using a very specific example, like a video editing scenario you brought.
Right. We had this listener, and they were really agonizing over choosing between, say, a 4070 or maybe pushing to a 4070 Ti. And their goal was upgrading for 2K video editing. The workflow sounds pretty standard, actually.
Yeah, about an hour timeline, probably game highlights, that kind of basic format video, nothing too crazy.
Okay, so the immediate thing, the crucial insight here, for that specific workload.
Both of those cards.
The 4070 Ti.
They're likely extreme overkill, really overkill.
So if you're spending that extra money, that, 5 or 6 million currency jump to get the Ti, you're basically buying horsepower that's just going to sit idle most of the time.
90% of the time, easily. Especially if your main bottleneck isn't raw compute power in the first place for that task.
Okay, explain that. How does that work with video editing?
It really comes down to understanding hardware acceleration. You know, the video formats they're worried about, H.264, 4.2.0, H.265, 4.2.0, maybe even the 10-bit H.265, 4.2.2.
Right.
They rely almost entirely on the card's dedicated encoder engines. For NVIDIA, that's NVENC.
Okay, so it's a special part of the chip.
Exactly. And once you hit the maximum speed of that specific encoder block, just throwing more CUDA cores, more raw power at the problem, it doesn't make the timeline scrub faster. It doesn't make the final render time shorter.
Okay. It's like having, I don't know, a dedicated high-speed lane on the freeway.
That's a great analogy.
When your car's in that lane, adding more lanes next to it doesn't make your car go any faster.
Precisely. And these modern encoder blocks, especially in the 5000 series cards, or even the good integrated ones like Intel Arc, they are incredibly fast already.
And we should also think about newer codecs, right?
Yeah.
Like AV1.
Good point. Even if the listener moves to AV1 encoding later, the dedicated AV1 hardware block in modern GPUs handles that efficiently too. It's separate from the main processing core's power.
So you're just hitting the ceiling of that specific part, the encoder.
You got it. And this ties directly into the VRAM question too.
Yes. Does more VRAM help here?
For a 1-hour 2K editing timeline, 12 gigabytes of VRAM isn't just enough. It's bordering on excessive for the editing task itself.
Really? 12 GB is plenty.
Ample. The only reason you'd really need to push for 16 GB on a higher tier card is if you were immediately going to pivot into, say, complex AI training or really large 3D modeling.
Okay, where the VRAM itself becomes the hard limit.
Exactly. But for straight video editing like this, that extra VRAM gives you basically no measurable benefit.
So the financial decision seems pretty clear then. Pushing the budget, doing that for a 4070 Ti over a 4070 for this specific editing job.
Means paying a huge premium.
For zero actual utility.
Right. The trick is knowing when that little extra spend actually gives you something tangible back.
Because there is a right way to push the budget sometimes, isn't there?
Oh, absolutely. We're not saying be completely stingy. We're just advocating for, strategic spending.
So when do you recommend doing the CA?
We only really recommend it when the cost jump is, let's say, marginal, but the value you get back is genuinely significant. Hitting that sweet spot before the returns diminish too much.
And we need to define marginal. What are we talking about cost-wise?
Maybe a difference of, say, 2 to 3 million currency, not that 5 to 6 million jump we just talked about. That's too much for little gain.
Okay, 2 to 3 million. And that needs context too, right? Against the whole build cost.
Crucially, if you're building, say, a 30 million currency PC overall, that 2 to 3 million difference is only about 10% extra.
Right, that feels more manageable.
It's a small push, doesn't put huge financial strain on you, especially when you think about how long you'll own the component.
And that 10% extra cash should get you a GPU that's truly deserved, as you put it.
Yeah, exactly. Think about moving from a solid mid-range card to the one just above it, maybe going from like a 5060 Ti up to a full 5070.
What does that typically unlock?
Well, that step often unlocks a really critical feature. Maybe it doubles your ray tracing performance, or it lets you reliably game at a higher resolution for future titles.
Okay, so a real noticeable jump.
That's a performance jump worth that small price increase. The rule is kind of. Marginal cost increase should give you a non-marginal tangible performance boost in the areas you actually care about.
And sometimes the smartest optimization is actually looking down, not up. The reverse push, maybe.
I like that. Yeah, absolutely. Yeah. Instead of agonizing over the 4070 Ti, you might realize you can go lower and still meet every single demand.
Like if 2K editing is the only really demanding thing you do?
Our source material suggests actively considering a lower cost card that's perfectly suitable, like maybe a 5060 or even an older gen card, if budget is the absolute top priority.
That really emphasizes suitability over just raw power or future-proofing that you might never use.
Precisely. By picking the component that perfectly meets your current needs and maybe your immediate future needs, you could save tens of millions of currency potentially.
And that saving is way more beneficial than chasing some theoretical performance ceiling you don't actually need.
Infinitely more beneficial.
Okay, so the takeaway is simple. Pushing the budget. It's only valid when a small extra cost unlocks a much bigger jump in usable performance.
Right. Otherwise, you're not paying for utility. You're paying for status, maybe. And in video encoding, status doesn't make those dedicated silicon blocks run any faster.
Okay, perfect. Now let's shift gears. Let's talk about that huge source of anxiety that stops people using the power they paid for. The fear of the 99% load.
Yes, the classic fear.
We had a listener worried that their GPU running at max clock speed, 99% utilization, that it's damaging the card over time.
And this is where we see that great inversion of expectation. It's fascinating.
What do you mean inversion?
Well, think back maybe a decade. Running something at 99% load did feel like you were pushing its limits, maybe risking something.
Yeah.
But today, because thermal engineering is so much better, the vast majority of PC users, especially gamers, they want to see 99% GPU utilization.
Really? They want it?
Oh yeah. If a gamer sees their GPU usage hovering around like 95% or lower, they immediately start troubleshooting. They think, oh no, my CPU is bottlenecking or my drivers aren't optimized.
So seeing less than 99 is frustrating now.
For many, yes. The aha moment is understanding the design philosophy. The card isn't just able to run at full load.
It's designed to.
It is literally designed to hit 99% load and sustain it safely. Seeing that number just means you are efficiently getting the maximum value from your big investment.
Because all the thermal limits, the TDP, the boost algorithms, they manage it.
Exactly. They're all designed to keep the card running as close to that performance ceiling as possible without ever exceeding safe operating temperatures. It's working as intended.
It's a sign of a well-balanced system, maybe.
It often is. But, and this is crucial, we absolutely have to differentiate between different kinds of heavy load. They are not all equal.
Okay, how so?
If you're gaming or rendering or using professional apps, even for, say, 8 hours a day, the card will be fine. It'll remain durable.
Why? Isn't that heavy use?
It is, but high utilization in those cases is managed. The card gets breaks. There are loading screens, menus, moments where the graphical complexity drops. The silicon gets these tiny momentary rests. It breathes.
Okay. It's not constant, nonstop maximum effort.
Exactly. Now contrast that with the real stress tests, things like AI training, complex machine learning, or historically cryptocurrency mining.
Right.
Those tasks are fundamentally different. They demand sustained, constant, just a monolithic calculation, running 24/7, maybe for weeks or months on end.
Okay.
That puts a fixed, nonstop, 100% load on the silicon. It generates a constant thermal curve that really tests the endurance of every single capacitor, every solder joint. Gaming just doesn't compare to that kind of relentless duty cycle.
That makes sense. So gaming at 99% is fine, but mining at 99% for months is where the real wear happens.
Precisely. And to really nail down this whole load management idea, we need a clear analogy. Let's compare running your CPU or GPU versus running your power supply unit.
Okay, the PSU. This distinction confuses a lot of people, I think.
It really does. And it's where the anxiety should actually be focused.
So running your CPU or GPU at 99% load?
That's optimal. That's desired. It means the hardware is working efficiently, giving you peak performance. You paid for all that capability. You should aim to use it safely.
Okay, got it. CPU, GPU at 99% good.
However, running the power supply unit, the core electrical component, at 99% of its rated capacity.
That's bad.
That is genuinely dangerous, and you should avoid it at all costs.
Why is the PSU different?
Because modern high-end GPUs especially are notorious for something called transient load spikes or power excursions.
Okay, what are those?
They're these instantaneous massive spikes in power demand that can momentarily shoot way above the card's official TDP, its rated power draw, just for a split second.
Like a sudden burst of effort.
Exactly. And if your PSU is already running near its limit, say 99% load,
It can't handle that sudden spike.
right, it can't maintain consistent voltage, you get ripple, components get stressed, the system might become unstable or worse.
Catastrophic failure. Pop.
Potentially, yes. That's why we always recommend a substantial buffer for the PSU, like 20 to 30% overhead capacity.
So if your system needs 600 watts, get maybe a 750 or 850 watt PSU.
Exactly. It needs that reserve capacity to safely handle those instantaneous power demands without stressing its own internal components, its capacitors.
Okay, so the takeaway is crystal clear. If you see 99% GPU utilization,
Feel good, you're getting your money's worth.
but if you see your PSU is pushing 99% of its rated wattage based on your system draw,
That is the component you need to worry about. That's the one to consider upgrading urgently.
Shift the worry from the calculator to the power delivery.
Perfectly put.
That's a perfect transition, actually. Because speaking of managing components under extreme load, that leads us right to heat, doesn't it? And the anxiety people have when they spend big money on fancy cooling solutions. Let's dive into some misconceptions about advanced GPU cooling, especially the ones using liquid. They seem to cause more confusion than comfort sometimes.
Oh, definitely. We saw a listener who'd invested in a really high-end card, maybe like a Giga 5090 Extreme with its own built-in liquid cooler and AIO. And they had two main worries. First, the classic one, the fear that it's engineered to fail the day after the warranty runs out.
The ticking time bomb theory.
Exactly. And second, just deep confusion about the difference between liquid metal and the water coolant inside.
Okay, let's hit the warranty first. Is there any truth to that idea that manufacturers build things to break right after the warranty expires? Planned obsolescence.
It's an anxiety that comes from, well, corporate reality, but its effect is grossly exaggerated. Failures tend to follow what engineers call the bathtub curve.
The bathtub curve.
Yeah, you get a higher rate of failure early on, that's infant mortality. Then there's a long period of very low random failures. And finally, the wear-out phase, where failure rates start to climb again as components age.
Okay.
Now, manufacturers definitely optimize warranty periods to balance their liability against the expected lifespan. That's just smart business. But the actual chance of a high-end component failing, like the day after warranty, it's statistically tiny, well under 1 or 2%.
Because the components themselves, the materials, are just better now.
Much more robust. The natural wear-out phase, where things like capacitors might dry out or solder joints fatigue, that's typically way beyond the standard 3-year warranty these days.
So don't plan your upgrade cycle based purely on warranty fear.
Please don't. Now let's clear up the liquid confusion. This causes a lot of stress for people with these fancy AIOs. The user heard their card uses liquid metal and others use water, and they got them mixed up.
Okay, they're totally separate things, right? We need to be precise. What is liquid metal and where is it?
Okay, liquid metal. It's a high-performance thermal interface material, a TIM. Think of it like the ultimate thermal bridge.
A bridge.
Yeah, it's this highly conductive fluid, usually gallium-based, that sits as a super thin layer directly between the tiny silicon die of the GPU itself and the copper base plate of the cooler that touches it.
Instead of normal thermal paste.
Exactly. It replaces standard thermal paste because it conducts heat way better. It can drop temperatures by several degrees, sometimes quite dramatically.
So it's just that tiny connection layer. It's not the liquid you see in the tubes.
Precisely. That liquid in the tubes is the water or coolant. That's the bulk cooling system.
What's in that? Just water.
Usually distilled water mixed with additives, things like special glycols to stop corrosion, and biocides to prevent algae or bacteria growing in the loop. And that liquid circulates inside the sealed AIO loop. It absorbs heat from the base plate, carries that heat energy away to the radiator.
Where the fans blow the heat off.
Exactly. So the liquid metal TIM and the circulating coolant, they never actually touch. Zero physical contact.
That's a really important clarification. One transfers heat from the chip super efficiently, the other carries it away.
You got it. Now, about the fear of failure in these integrated AIOs themselves, where's the weak spot?
What usually breaks?
Almost always the primary failure point is the pump.
The little motor pushing the liquid.
Yep. When the pump motor fails or gets clogged, the coolant stops moving. Heat transfer stops dead. The chip overheats incredibly fast.
And the system shuts down.
Usually triggers thermal throttling or an immediate shutdown, yeah. Now, for a standard CPU AIO, replacing the whole unit is pretty straightforward. But for an integrated GPU AIO, it's way more complex and expensive.
What about the old nightmare scenario? The tube bursting and leaking coolant everywhere.
Yeah. That was a legitimate fear with the very first generations of aftermarket AIOs. Maybe 10, 12 years ago.
But not anymore.
Not really. Modern AIO tubing is engineered with multiple layers, really durable materials like FEP fluorinated ethylene propylene or similar stuff. They're extremely durable.
So less likely to just spontaneously burst.
Highly unlikely, assuming it was installed correctly and hasn't been physically damaged or strained. Those tubes are generally very reliable and often last much longer than the warranty period.
Okay, let's talk about the market context for these really premium built-in GPU AIOs. We're talking cards costing, what, 30, 40, 50 million currency or more?
Yeah, flagship territory.
Does that price tag actually buy you better reliability in the cooling?
It provides a massive incentive for reliability. Think about it. Manufacturers invest way more in the quality control for their absolute top-tier products.
Because the customers are different.
Exactly. The people buying these 5090 level cards are often high net worth individuals or professional studios. They demand flawless performance and uptime.
Oh, can't afford downtime.
Right. If a manufacturer got a reputation for their flagship cooler pumps failing or tubes leaking, they'd destroy brand trust with their most valuable customers.
And the cost of recalls or repairs on those units would be huge.
Immense. So the initial quality assurance, the testing, it has to be absolutely top-notch.
And do we have evidence this actually works? Are these high-end integrated AIOs reliable in the real world?
Our professional experience strongly suggests yes. Failures in these high-end, factory-integrated GPU AIOs are exceedingly rare now.
Really?
Yeah, since around 2019, maybe even earlier, the number of returns we've seen for pump or tubing failure on these top-tier cards has dropped to basically zero. They are, by design and by market necessity, exceptionally robust.
Okay, but let's imagine the worst case. It does fail, maybe just outside warranty. What does that high-end user typically do? Budget isn't their main constraint, right?
Right. They usually go one of two routes. First, the simplest, just replace the entire graphics card, get the latest and greatest again.
Okay, option 2.
Option 2, especially popular with enthusiasts, is customization, because these cards are often built on reference PCB layouts.
The circuit board is standard.
Often, yes. So they can actually remove the entire integrated AIO cooler shroud and replace it with a third-party custom water cooling block.
And loop it into a bigger custom system.
Exactly. Integrate it into a full custom loop. The high-end PC community always finds a way to reuse and customize expensive hardware. There's always a solution if you're willing to tinker.
Excellent. Okay, we've gone from fear of paying too much to fear of using it too much to understanding these complex coolers. Now, let's shift to a really practical decision point. The head-to-head battle between two very capable cards at a more accessible price. Let's pit the modern RTX 5050 against the old VRAM workhorse, the RTX 3060.
This is a great comparison. They often sit around that 6 million currency mark, right?
Yeah, forcing a really interesting choice that depends entirely on what you do with the card.
This is probably the most fascinating trade-off in the current market, I think, because you are literally choosing between raw capacity of the VRAM and modern tech features. It forces you to define your main bottleneck.
Okay, let's break down the core performance differences first.
Yeah.
The 5050, it's newer, Ada Lovelace architecture.
Right, more efficient cores, higher clock speeds usually.
So for just pure full HD gaming, 1080p, the 5050 is a bit stronger.
Generally, yes, slightly stronger in raw rasterization at FHD. However, if you push both cards to native 2K or even 4K resolution.
Without any upscaling tech.
Exactly, just raw pixels. The 3060, often having a wider memory bus, can sometimes pull slightly ahead in that traditional frame rendering.
But, and this is a big but.
Both cards really struggle at native 2K, 4K and demanding games, don't they?
Oh yeah, they're not really designed for that natively.
And that weakness in native high-res performance is precisely why the technology advantage of the 5050 becomes the critical factor for many gamers.
You mean DLSS?
Exactly. The 5050 supports the absolute latest DLSS 4 and, crucially, its multi-frame generation capability.
Okay, explain frame generation quickly.
DLSS uses AI to upscale lower-res images, but FrameGen actually inserts entirely new AI-generated frames between the traditional re-rendered ones, and NVIDIA's quality is generally seen as superior to open-source alternatives like FSR.
So this frame generation is like the 5050's secret weapon.
It's superpower, yeah. It effectively lets a card marketed for FHD gaming play modern, demanding games smoothly at 2K resolution.
Even though it's not powerful enough to render 2K natively that well.
Right. You trade a bit of native rendering speed for this really refined AI upscaled and generated experience. For a gamer focused on smooth gameplay at higher resolutions, that tech leap gives immediate tangible benefits the 3060 just can't match.
Plus, there's the efficiency factor, right?
Huge factor. The 5050 is significantly more power efficient, lower TGP total graphics power.
What means?
Often means it only needs one auxiliary power connector from the PSU, and you can sometimes get away with a simpler, cheaper 500-watt power supply for the whole build.
Ah, so it can save you money on the PSU and maybe make the build simpler.
Definitely. It can shave off cost and complexity.
Okay, so strong case for the 5050 for gamers, especially with DLSS 4 and FrameGen. But then, there's the 3060.
The old reliable.
Its entire relevance, years after launch, seems to rest almost entirely on one thing, that VRAM lifeline.
The 12 gigabytes of memory. Yep.
Let's be clear, though, for gaming. Is 12 GB actually useful on a card at the 3060's power level?
Often, no. It's frequently excessive for its own processing power in games. The GPU core itself usually can't render fast enough to actually fill all that memory in most current titles at reasonable settings.
So the extra VRAM doesn't help gaming performance much?
Not usually, no. But that VRAM becomes absolutely critical the second you shift your workload away from gaming.
Ah, okay. This is the so what moment. This is where the choice gets made.
Exactly. It depends entirely on your application.
So let's lay it out. If your main goal is pure gaming,
50/50 is the preferred choice. Modern architecture, better efficiency, and that game-changing frame generation tech for higher resolutions.
okay, what if it's video editing or maybe basic 3D rendering with, like, smaller models?
50/50 is generally better there too. Its newer codec engine, the updated NVNC block, processes video encodes and decodes faster than the older one in the 30 series. It's surprisingly quick for editing at its price point.
Okay, 50/50 wins for gaming and light production. When does the 3060 become the necessary choice?
Now the script flips completely. If your workload involves AI, running large language models, or really complex 3D graphics,
Like what kind of 3D?
think high-resolution sculpting in Blender or ZBrush, complex texturing work with lots of large maps, or handling massive architectural or urban planning models, things that need to load huge amounts of data into memory.
That's where the 12 GB VRAM is essential.
Absolutely essential. It is the non-negotiable limiting factor for those tasks.
So the 3060 might be slower in terms of raw chip speed compared to the 50/50.
Yeah, the actual calculations might take longer.
But the 12 GB VRAM lets it actually load and handle those massive data sets or the simultaneous processing needed for AI.
Exactly. Running advanced stable diffusion models, working with huge scenes in Unreal Engine, or training certain types of neural networks, they require memory capacity the 8 GB typically found on a 50/50 simply doesn't have. It just crashes or refuses to load.
So the 3060 is the practical utilitarian choice then. The Duck-Vit card, as the source material perfectly put it.
That's the perfect description. It might be slower, it might chug along, but it can get the job done when VRAM is the absolute bottleneck.
While the 50/50 is the pick for efficiency and maximizing modern gaming and encoding tech.
You have to weigh VRAM capacity for those specific memory-hungry tasks versus the generational tech improvements for speed, efficiency, and features like frame gen.
That lays it out beautifully. A clear decision tree based on workload. Okay, let's pivot one last time to maybe the most fascinating part of this whole deep dive.
The anomaly?
The hardware anomaly. This highly improbable technical edge case that makes us question what disabled hardware really means.
This is pure lightning strike territory, a convergence of unlikely events.
Tell the story again. What happened?
Okay, so a user installed an Intel Core i5-14600KF CPU. Now that F is critical. It means the integrated graphics, the iGPU, is supposed to be permanently disabled at the factory.
Can't use it.
Shouldn't be able to. But this user took out their dedicated graphics card, plugged their monitor cable directly into the motherboard's video output.
Which should do nothing with an F-series CPU.
Right, but they successfully got a video signal on their screen.
Wow. An impossible feat, technically.
Yeah.
But what was the result? Was it usable?
Usable, not even close. The outcome was fascinatingly bad. A painful 4 frames per second in League of Legends.
4 FPS.
And simultaneously, the CPU utilization instantly spiked to 100% across all cores.
Okay, we have to figure out the chain of events here. How did a disabled chip manage to display anything, even 4 FPS?
To get it, you need to peek behind the curtain at chip manufacturing. Intel makes these CPUs starting from a single complex wafer design, often based on their top-tier i9 architecture.
Okay.
During quality control testing, if they find flaws, maybe a few processing cores don't work right, or the integrated graphics processor itself is faulty, they don't physically cut those bits out.
I just switch them off.
They disable them using internal, permanent hardware locks. Think of them like tiny digital circuit breakers they flip during production. This is how they create the lower tier i7s, i5s, or the F series, where the iGPU is locked off.
So the iGPU silicon is still physically there on the chip die?
Absolutely. It's present, just locked, and it should be completely invisible and inaccessible to the system software.
Okay, so the first, simplest guess, the good fluke theory, is that quality control messed up. And this F-series chip just accidentally shipped with a fully working iGPU. The lock failed.
We can dismiss that one immediately.
Why?
because of the performance. If the iGPU had been fully functional, even an older Intel iGPU wouldn't be great, but it certainly wouldn't be 4 FPS in League of Legends. It would be much, much better than that.
Right. The terrible performance proves the main graphics cores were successfully disabled.
Exactly. They were locked and dead to the world.
So if the graphics cores were dead, what part was sending this signal? This is the core puzzle.
The answer lies in understanding that the iGPU isn't one single block. It's internally segmented.
It has different parts.
It has 3 main components, broadly speaking. You've got the graphics cores themselves, doing the 3D calculations. You've got the codec engine for video encode, like we talked about earlier. And then there's a separate, highly specialized unit called the display engine.
The display engine, what does that do?
Think of the display engine as the chip's dedicated mail carrier for visuals. Its only job is to manage the signals going out to the physical monitor ports, HDMI, DisplayPort, etc.
I see. So Intel successfully locked the heavy lifters, the graphics cores, maybe the codec engine.
Right.
But the mail carrier, the display engine, maybe it wasn't faulty on this specific chip, and critically, maybe a lock for it failed, or it uses a different locking mechanism that wasn't tripped.
That's the hypothesis. The display engine itself was still physically working, and here's where the software chaos meets the hardware flaw. A rare flaw, maybe an unpatched bug, in the specific motherboard BIOS software, combined with the presence of that still active display engine. It allowed the operating system, Windows in this case, to somehow detect that something capable of sending a display signal was present on the CPU bus.
So Windows knocked on the door, saw a valid output path, but when it asked, okay, who's going to render the 3D graphics for this game?
Silence. The main graphics cores were locked and didn't answer.
So what did Windows do?
It couldn't load the proper optimized Intel graphics driver because the hardware wasn't fully there, so it was forced to fall back to the absolute most basic, rudimentary option available.
Which is?
The generic Microsoft Basic Display Adapter driver or a similar software renderer.
And that software driver is why the performance was so abysmal and the CPU hit 100%.
That is the ultimate price of this weird hardware-software fluke. That generic software driver forces the main CPU cores, the powerful processing cores optimized for fast sequential math to handle all the graphical calculations, which are inherently parallel tasks.
It's using the wrong tool for the job, massively inefficiently.
Extremely inefficiently. It's like asking a mathematician to paint a mural. They can do it pixel by pixel, but it will take forever and use all their energy. That's why a powerful 14-core CPU maxed out completely just to render a crippling 4 FPS. The CPU was forced into doing graphical work it was never designed for.
Wow. So this anomaly is truly a perfect storm, a unique combination of a partial CPU locking fault, a specific motherboard BIOS loophole, and Windows falling back to a generic software driver.
Absolutely. It has zero practical value for anyone. You can't use it. But it gives us this fascinating glimpse into the layered complexity of modern silicon and how software vulnerabilities can sometimes unintentionally expose hardware functionality that's supposed to be hidden.
It's a profound reminder, isn't it, that disabled doesn't always mean gone. It just means locked. Okay, this has been an incredibly detailed deep dive. We've gone from the philosophy of spending to the nitty-gritty of hardware functions. We started with the whole financial side of cool, right? Defining when an upgrade is actually worth the extra cash and when it's just, well, wasteful overkill for something like a basic 2K video timeline.
Yeah, and we flipped the script on load anxiety. We established that seeing your GPU hit 99% should actually make you feel good you're getting value. But we warned that the real danger zone is pushing your power supply unit too close to its limit. That's where the worry should be.
Right. And we demystified those high-end liquid coolers too, clarified the very different jobs of liquid metal TIM and the circulating coolant, and surprisingly confirmed the pretty solid quality control on those expensive integrated AIOs.
And then we tackled that key decision, 50-50 versus 30-60. We laid out a clear workload-based choice. Do you need modern efficiency and frame generation for gaming and light work? Or do you absolutely need that 12 GB VRAM for huge data sets in AI or complex 3D? Your specific bottleneck dictates the right card.
Which brings us back to that anomaly. Let's end with one final, maybe provocative thought that builds on that weird, a 14-ton 600KF story.
Okay.
The fact that the display engine was still functional enough to be, well, accidentally exploited by a software fallback, does that raise bigger questions about hardware locks?
How so?
Like, Could this accidental 4 FPS output hint at a future where maybe hackers or dedicated enthusiasts or even sophisticated malware could find ways to bypass BIOS or driver protections to unlock other supposedly disabled hardware features, turning an i5 into an i7, or enabling parts of a chip that failed testing?
That's a heavy thought. The potential for unlocking latent functionality.
Or maybe more broadly, does it just imply there are these fundamental, maybe unknown vulnerabilities in how the BIOS and drivers interact? Gaps that unintentionally bypass what the manufacturer intended, letting disabled bits cause instability, or, like here, generate a gloriously slow-motion slideshow.
It definitely makes you wonder about the true security and integrity of those hardware locks when software layers get involved. It's something significant to consider next time you just hear a hardware component dismissed with that simple word. Disabled.
Food for thought. Thank you for diving deep with us today.
If you enjoy this video, please like, share, subscribe, and hit the bell to the later update from my channel. Thank you for watching till the end, and see you in the next video.